This is intended to be a brief overview of some of the issues that you'll typically encounter when dealing with longitudinal data. From time to time, I'll intentionally oversimplify things. One theme of the presentation is that the best practical approach to longitudinal data is to visualize what you want to do, and then find a statistical technique that does what you want, rather than assuming the analysis will follow a single protocol, and then trying to shoehorn what you do to fit the requirements of that protocol. That said, I'll briefly describe mixed models and repeated measures methods, as these are terms that you've encountered in the literature. The data array for mixed models analysis is long and thin. In other words, it has one record per patient per time point, rather than just one record per patient. In the slide, these two patients have different numbers of records, some at the identical time points of 0 and 60 days, and some at different time points. Time points don't have to be identical, which is one of the advantages of the mixed models approach. Predictor variables are patient and time, where time is the predictor of primary importance, and patient is of secondary importance and just needs to be controlled for. Patient enters the model as something called a random effect, which simply means that the inference will extend beyond the specific patients in the study. This is in contrast to a fixed effect, such as intervention group in a randomized trial. There, the inference only extends to the specific interventions being considered. The data array for repeated measures analysis looks different. Short and fat with one observation per patient. The Y1 through Y3 denote the outcomes at 3 specific time points. For repeated measures analysis, you need complete data. In particular, a patient that's missing on any one of the time points will be dropped from the analysis. For a modest number of missing values, there are workarounds, for example, using imputation. But realistically, a repeated measures analysis will only work well if the data are complete, or nearly so. When trying to decide what to do with longitudinal data, I ask two triaging questions listed on the slide. Sometimes the answer to both questions is no, in which case I'll need to use more sophisticated analytical techniques than we'll be discussing here. Fortunately, most of the time, one of these questions can be answered in the affirmative. First question is essentially asking whether I can perform a repeated measures analysis or something like one. This slide illustrates the basic idea behind a repeated measures analysis, using the simplest possible case of just 2 time points. These 2 time points are transformed into a single difference score. To extend the idea, 3 time points can be transformed into 2 different scores, 4 time points can be transformed into 3 different scores, and so forth. Recalling that all statistical tests compare signal with noise, in this slide there's a consistent signal that the intervention between pre and post has led to a small but consistent reduction in systolic blood pressure. It's drawn the estimated signal is approximately 7.5. Now take a look at the middle column for post-systolic blood pressure. It's quite noisy, with values ranging from 100 to 150. A test that compares the signal to the noise at the post-test might not be able to declare that the signal is statistically significant. Also notice that most of the noise at the post-measurement is due to the heterogeneity of patients at baseline. By creating the difference score, we've let each patient service their own control and eliminated the noise due to baseline differences. Difference scores are much less noisy than the post scores. The statistical test will be more powerful. The name for the specific statistical test is a one-sample pair t-test. Paired tells your audience that you've created difference scores. In this context, it will be obvious that the differences compare pre and post. The one sample says you're comparing the mean difference score from the entire group against 0. In contrast, a 2-sample pair t-test would first create difference scores for intervention and control patients, and then compare these 2 group means. This slide reviews the rationale for having each patient service their own control. Using this logic, the ideal case should be obvious, as summarized on the next slide. Creating different scores works best when patients are heterogeneous, but then the impact of an intervention's effect is consistent across patients. In this case, a different score will have a signal and relatively little noise, thus the statistical analyses will be well powered. In a typical QI application, you'll either have 2 or 3 time points, depending upon whether you want to assess whether the impact of your intervention, typically some change in the system of care, is permanent. In that case, each of the difference scores has a natural interpretation. For example, the difference between the first 2 time points quantifies the short-term impact of the intervention. get the same answer regardless of which two different scores you create. Many but not all analysts would adjust the 2 or 3 pairwise comparisons to account for multiple testing, for example by dividing the standard 0.05 by the number of tests. One thing that specialists in repeated measures analysis worry about is the structure of the correlations among the outcome variables. They use subtly different statistical approaches depending upon which correlation structure is assumed. For our purposes, this is a second-order issue that needn't concern us. The second triaging question essentially asks whether it can radically simplify the analysis by turning the multiple observations in each patient into a single one. If so, we've reduced the dimensionality of the data. Here's an illustration of the idea. The clinical concept of good death has been operationalized by plotting quality of life over time, and then summarizing this plot by the area under the curve. The idea works well if the quantitative summary has two properties. First, that at least roughly captures the desired concept, and second, that it can be well estimated from the data. More about this latter point in a moment. At the end of the day, the derived data array will have one record per patient and one outcome per patient. In essence, once area under the curve has been calculated, we forget it was derived from multiple data points and treat it as if it were a single number. In IT lingo, the area under the curve has been created by rolling up a data array with one record per patient per time point. Here are some examples of typical summary measures. Some use all the data points in their calculation. For example, area under the curve does this, as does slope of a regression line. Others use a single data point, such as maximum value. As an example of checking the data to see whether the summary measure makes sense, the slope of a regression line is a good match for the underlying concept. You'd still need to plot the data for a sample of individuals to reassure yourself that their data in fact do follow straight lines. If not, the next step would be to ask whether another measure can be found that's still conceptually sound, but also more closely follows the data. The default is to take the above data array and treat a data point as a data point as a data point, despite the fact that some patients will provide more and better data than others. Some other options for dealing with this situation are to drop patients with sufficiently poor data to give more weight to the better of observations. Most statistical procedures have a more complicated version that takes weighting into account. As an example, suppose you're going to change the system of care to improve the quality of anticoagulation management. Comparing pre-intervention, immediate post-intervention, and long-term post-intervention time points, it seems like a reasonable thing to do, and perhaps each of these could be calculated over 6-month intervals. The data array would be short and fat, consistent with the repeated measures analysis, which within each time period you need a summary of the quality of anticoagulation. Typically, people use percent time and target range obtained by linear interpolation. The calculation is illustrated in the next slide. The x's denote the observed INR values. We simply connect the dots to obtain an INR for any particular day. The percent time and target range is the percentage of days within a central corridor. Some things that can go wrong with this calculation are listed in the previous slide. The interpolation doesn't make sense if there are very long intervals between INR measurements. Indeed, very long intervals might in and of themselves indicate problems in quality of care. Small departures from target range are treated the same as large ones, despite the fact that the risk curve is U-shaped, with large departures being particularly worrisome. An ideal summary measure might set a requirement about the interval between measurements, attach a risk score to each day based on the distance from the target range, and then average these risk scores. Alternatively, in general practice, percent time and target range might be sufficient, and it's certainly simpler to calculate. In any event, we can now fill in the data array with percent time and target range within each interval, or some other measurement that plays the same role. We closed our session with a discussion of the sort of QI applications that could be supported by a longitudinal collection of patient-reported outcome data. Key insight was the need to accommodate the fact that the measurement schedule for patients will be irregular, suggesting that the best way to proceed might be to ask how the multiple observations per patient could be boiled down